We're going to look at inclined planes. So this is going to be drawing our free body or force diagrams when our object is on an angled surface. Okay, so we're going to start off with this example. Here we have a box sitting on a ramp at a 30-degree angle. We want to draw what the free body diagram would look like on this block. So I know I'm always going to have my force of gravity pointing straight down. Okay. I'm also going to have a normal force, so that's force that's caused by the contact with the surface of the ramp. And remember, that always points perpendicular to that surface. So since my surface is angled, my normal force is also going to be up at an angle. And then if it's sitting motionless, that means I need something acting on this block, preventing it from sliding down. And that's going to be my force of friction. Remember, friction always points parallel to our surface, opposite the direction of intended motion. So here, our block would want to slide down, which means my force of friction is then going to point uphill. Okay, so I'm going to pull that free body diagram off to the side a little bit so it's easier to look at. So we had our force of gravity straight down, our normal force going up and to the left since our surface was angled, and then our force of friction pointing uphill. And that's what's preventing our block from sliding down. So if we look at this, the way that our free body diagram is drawn right now, we have two forces at an angle. We have this normal force and our force of friction. To make this a little bit easier to look at, we're going to re-visualize this so that only one force is at an angle. So how we are going to visualize this is by tilting our axes. So if we look at this graph over to the right, normally when we look at our coordinate plane, for our axes, we have one vertical axis and one horizontal axis. Okay. To make this a little bit easier to work with, we are going to just tilt that axis so that our x-axis is now up at an angle, as is our y-axis. Okay, so when we're looking at this free body diagram, we're going to consider our x and y-axes to be tilted. So now that when we look at this, we really only have that force of gravity that's not perfectly lined up with our new rotated axis. Okay, so I know that's a little funky, but it's going to make it easier to work with because now it's only that force of gravity that doesn't line up with our new axis. Okay, that normal force lines up on our y, force of friction lines up on our x. Okay, and then it's really only that force of gravity that does not match up with that. Okay, so the reason why this is really nifty is, here, let's get rid of those, is that now we can start applying some different values to this body diagram. Angle, we have our force of gravity at in relation to this new axis. What we can do is we're going to continue on down opposite of our normal force. Okay, so that will tell us our y component of our force of gravity because that lines up with our new y-axis. And then that horizontal component lines up with our new x-axis, and that'll be our force of gravity in the x direction. Okay, so just like what we did earlier, we can break up that angled, and I'm putting angled in quotation marks, force into its horizontal and vertical components so we can see how much of that force of gravity is pulling our block downhill and how much is pulling down into the right. Okay. All right, so what's really cool that we can do here is actually the angle that we have here in the bottom of our triangle, that's going to be the angle that we have our force of gravity at. So after we continue down from that normal force to break up that force of gravity, that upper right hand or the upper angle of that triangle is going to be the same angle as our angle of incline. Okay, if you guys want to know why that is the case, please come see me and I'd be happy to walk through the geometry of that. Okay, but again, we can see how much that force of gravity is angled from our new y-axis just by looking at the angle of incline. Okay. So now that we have our free body diagram labeled, we can start to look to see what forces are equal. Okay. So if we look at this, we're always doing it in relation to our new x and y axes. Okay. So if we look at our force of friction, our force of friction points uphill, points up and to the right. We want to see if we have any forces pointing down and to the left. And we do. We're going to see we have this force of gravity in the x direction also pointing down and to the left. So that means those two are going to be equal. Okay, so that force of gravity component that's pulling our block downhill has to be equal to the force of friction that's holding that block uphill in order for our object to be balanced and remain motionless. Likewise, if we look at our normal force, we can see pointing in the exact opposite direction of that normal force is that force of gravity in the y direction, or that vertical component. So we can also say that our normal force is equal to that force of gravity in the y, okay, because we only have one force pointing in either direction. Block has a mass of 10 kilograms, and we want to find all the forces acting on the block. So we want to find our force of gravity, force of friction, and our normal force. I redrew a free body diagram down here in the right-hand corner just so it's a little bit easier to view. And remember, we break up that force of gravity into our y and x components by continuing down from that normal force. Okay, so first thing, if we know our mass, we know that we can find our force of gravity. Because if we do 9.8 times our mass, that will tell us the force of gravity pointing down on the object. So if we have a mass of 10, 9.8 times 10 will give us a force of gravity of 98 newtons. Okay, so that tells us the force of gravity acting on this block will be 98 newtons. Okay. All right, next, to find our other forces, we need to think about what components are going to be equal. So if we look uphill, downhill along our rotated x-axis, we can see we have one force pointing up and to the right and one force pointing down and to the left. Since I only have one force in either direction, that tells us that my x component force of gravity and my force of friction need to be equal to one another. Okay. So if I can find my x component, my force of gravity, I will be able to find my force of friction. In order to find my force of gravity in the x direction, I'm going to have to use a trig function. Okay, because if I look, I have a right-hand triangle with my force of gravity. I know my upper angle is 30, and I know my hypotenuse, or my actual force of gravity, is 98. So your actual force of gravity goes on your hypotenuse. So here, we would want to use sine of 30 is equal to opposite over our hypotenuse. And I would find that my force of gravity in the x direction is 49 newtons. But if I'm trying to find my force of friction points in the opposite direction. Okay, so my force of friction stands the same value since they're balanced, but my force of friction points uphill. So I would say my force of friction is 49 newtons uphill. Always make sure you include a direction with your value. Perfect. So then the last force we have to find is our normal force. So if we look, our normal force points up and to the left along our new y-axis. And directly opposite that normal force is our force of gravity in the y direction. Since we only have one force pointing in either direction, we know those two have to be equal to one another. So if we find our force of gravity in the y direction, we'll then be able to find our normal force. Okay? So if I look at my force of gravity in the y, again, I know my hypotenuse is my force of gravity, and now I'm trying to find my adjacent side, so I'm going to use cosine. So the cosine of that angle of incline, 30 degrees, is equal to my adjacent over my hypotenuse. Okay. So I'll multiply each side by 98, and I'll find that my force of gravity in the y direction is 84.87 newtons. However, I want to find my normal force. So my normal force, it's going to balance out the FTY, so it's going to have the same value, 84.87 newtons, but it points in a different direction. So for my normal force, I say 84.87 newtons. Okay. Perfect. So we're going to follow the same process that we did earlier. The only difference is that we're rotating our X and Y axes. So in this example, we have a box pulled at a constant speed up the frictionless ramp. The mass of the block is 15 kilograms. Our angle of incline is 41 degrees. And then this block is being pulled uphill by the weight of this ball on the other side of the pulley. So the first thing we want to do is find the normal force on that block. So as always, our first step is to draw our free body diagram. So we know for our free body diagram, force of gravity always points straight down. Okay? That one's always a given. The next one we're going to have is normal force, since our block is on a surface. And remember, normal force points perpendicular to that surface. So in this case, it's going to be going up and to the right, okay, because it needs to be perpendicular to the inclined plane. Okay? We also have a rope attached to that block that's pulling it uphill. So since we have a rope, we're going to have a force of tension pulling that block uphill. Here, our ramp is frictionless, so we're not going to include a force of friction in this diagram. Okay, so now that we have the forces down that are acting on our box, the next thing we need to do is find our X and Y components of our gravity, okay, or break it up into our X and Y. Remember, we always are going to continue down from that normal force when creating our triangle, okay? Now we can see how much of that force of gravity is pulling downhill or is acting in the X direction and how much is acting in a rotated Y direction, okay? And the reason why we want to continue down from that normal force is because now we can say that that angle of incline, that 41 degrees, is the same as the angle in the upper corner of my triangle. Okay, so now let's look and see what forces are going to be equivalent on this diagram. Okay, so always look around along your rotated X and Y axes. So if we look in a rotated X direction, okay, so uphill, downhill, we're going to see that we have one force that points uphill and one force that points downhill, the X component of our force of gravity. Since we only have one force acting in either direction, those two forces are going to be equivalent. Next, looking in our rotated Y direction, we can see that we have one force pointing up and to the right and one force pointing down and to the left. Since again, we only have one force acting in either direction, we can say that those two forces are equal in magnitude. Okay. So if we look at this, our goal is to find our normal force. Based on its diagram, we just saw that our normal force was equal to our Y component of our force of gravity. So if we're able to find the Y component of that gravity, we'll be able to find our normal force. Okay. So before we are able to find our Y component of that gravity, we need to find just our normal force of gravity. So we know our equation for force of gravity is going to be 9.8 times our mass. In this problem, it tells us that our box has a mass of 15 kilograms. So just do 9.8 times 15 to get that force of gravity. And we'll find that our force of gravity here is 147 newtons down. Okay? So 9.8 times our mass times our is equal to our overall force of gravity. So we're going to put that on our force of gravity vector in our free body diagram or on the hypotenuse of that triangle. Okay? Remember, the hypotenuse always tells you your actual overall value. Okay, now that we know our actual overall force of gravity, now we can see how much of that is acting in the Y direction. Okay, so we want to find the Y direction. We are looking at the side adjacent to our angle. Okay, so if I'm trying to find an adjacent side, I know I'm going to want to use cosine. So my force of gravity in the Y direction would be equal to 147 times the cosine 41 degrees. Okay. When I do this, I can find that my force of gravity in the Y direction is 110 newtons. Okay. So since my Y component is 110 newtons, that tells me my normal force is also 110 newtons. Okay, because we only have one force pointing in either direction. They're exactly opposite one another in direction, so that they have to have the same magnitude and balance one another out. Okay. I want to find the mass of the hanging ball. So here we're going to want to draw a free body diagram for that ball. All right, so on the ball we're going to have a force of gravity pointing down and a force of tension pointing straight up. If our system is moving at a constant speed, that means our upward force of tension and our downward force of gravity have to be equal to one another. We'll have one force pointing off in either direction, so they need to balance one another out. Okay, so we don't really have much information about the free body diagram for that ball just yet. However, we have a rope connected to a pulley. And remember, a pulley does not change the force of or the magnitude of our force. So that means the tension in this part of the rope is going to be equal to the tension in this part of the rope. Okay, so the pulley does not change the value of the force. The tension in either part is going to be the same. So that means if we can find our force of tension from acting on our box, then we'll be able to find our force of tension acting on that ball. Okay, so we have to revisit the free body diagram we drew for part A. If we look at that free body diagram, we can see that our force of tension points uphill and our force of gravity in the x direction points downhill. Since we only have one force in either direction, they need to be equal to balance one another out. Okay, so a force of tension is equal to that force of gravity in the x direction. So here, if I want to find the force of gravity in the x direction, I'm trying to find the opposite side of that triangle diagram, which means I would want to use sine to solve for that component of my force of gravity. We could say sine 41 is equal to my force of gravity x direction divided by 147. Multiply each side by 147 to get the force of gravity in the x direction by itself. And we'll find that FGX is equal to 96.44 newtons. That means our force of tension also has to be 96.44 newtons. Okay? Because we said they were equal in magnitude. Okay. So what that means is if our force of tension in this part of the rope is 96.44, our force of tension in a rope on the other side of the pulley also has to be 96.44 newtons. Because remember, the pulley does not change the value of the force. So looking at that free body diagram, force of tension points up, gravity points downwards. We said we were not accelerating, so those two forces have to be equal in magnitude. So once we know our force of gravity, now we're able to find our mass. Because we know our force of gravity is equal to 9.8 times our mass. And we just found our force of gravity is 96.44. So that means in order to find our mass, you're just going to want to divide each side by 9.8. And we will find the mass of this unknown ball is going to be equal to 9.84 kilograms. Mass is always going to be given or solved for in kilograms. Okay. Awesome. In this example, we have a box pulled up an incline with friction at a constant velocity. We want to find the force of friction acting on this box. Okay, and we know the mass of the block is 30 kilograms and the force of tension in the rope is 500 newtons. So go ahead and pause the video and try and draw what your free body diagram would look like for this box. When you have your free body diagram, go ahead and come back to check how you did. On the right. So we know force of gravity always points straight down, and normal force is always going to point perpendicular to our surface. Here, it looks up and to the left. Okay. We have a force of tension pointing up here, uphill, so we want a force of tension going up and to the right. And then friction always opposes our direction of motion. So if our box is moving uphill, then our force of friction is going to be pointing downhill. Remember, friction always points the direction opposite our object is actually moving. Okay. So on this diagram, we should have these four forces. And then we can break up that force of gravity into our X and Y components. Again, looking from that tilted axis perspective. Remember, when you're breaking or when you're creating that triangle, make sure you always go down from the normal force, because then that upper angle can be equal to your angle of incline. All right, let's look and see what equalities we can have in this this triangle or in this free body diagram. So if we look uphill, downhill first, so that new x-axis, we have one force pointing uphill. We have our force of tension. Okay. However, we have two forces pointing downhill. Since we have two forces pointing downhill, we need to add those together to equal our one force pointing uphill. Okay, so our force of tension, our force pointing uphill, would be equal to our two forces pointing directly opposite it. So that would be our force of friction plus our x component of our force of gravity, plus Fg. Okay, because we have two forces going downhill, we have to add those together to equal our one force pointing uphill. If we look in our new y-axis, or new y direction, we have one force pointing up and to the left. Okay, we have that normal force. And we only have one other force pointing in the exact opposite direction of it. That force of gravity in the y direction. So since those two forces are exactly opposite one another, and we only have one force in either direction, we're going to be able to say that those three. So normal force would be equal to our force of gravity in the y direction. Remember, we're using those rotated axes. Okay. So now that we have our free body diagram for this motion, go ahead and again, pause the video and try and solve for your force of friction. Okay, now that we have our free body diagram, see if we can set up this problem. And come back when you're ready. 0.45 newtons downhill for that force of friction. Okay, so let's work through how we wanted to get that value. In order to find our force of friction, we wanted to use this relationship. That our force of tension going uphill is equal to our force of friction plus our force of gravity in the x direction downhill. So our first step in solving this equation is we need to find what our force of gravity in the x direction is. How much of that force of gravity is pulling it downhill? So our first step is to use our force of gravity equation, that our mass times 9.8 is equal to our force of gravity. So we found that the overall, or the total force of gravity acting on this object is 294 newtons. Remember, we put our actual value on the hypotenuse of that triangle. Okay, so now if we look at our force of gravity triangle, we know our hypotenuse, or our actual value of force of gravity, is 294 newtons. If we want to find our force of tension, we want to find our force of gravity in the x direction. So if we want to find how much of that is pulling downhill, or opposite side of our angle, we're going to want to use sine. So in step 2, we now use that force of gravity and our trig function to find that horizontal component of our force of gravity. So we do our sine of 20 is equal to opposite over adjacent, or FGX over 294. Multiply each side by 294, and we find our force of gravity in the x direction to be 100.55 newtons. Okay. But our problem is looking to find force of friction. So again, we need to go back to this relationship. We know that our force of tension is equal to force of friction plus FGX. So now if we look at our problem, it tells us our force of tension is 500 newtons. So we're able to plug that in our equation. And we just found that FGX is equal to 100.55 newtons. So we plug in the values that we know into this equation, subtract 100.55 from either side, and we'll find that our force of friction then has to be 399.45 newtons downhill. I hope this helped. If you guys have any questions, please let me know. Otherwise, have a great day.